You are the bridge between innovation and implementation. We look forward to deeper collaboration that will enable us to scale these technologies and create impact at both the national and continental levels. To our students, I encourage you to listen actively, engage thoughtfully, and envision yourselves not just as learners, but as future innovators and problem solvers. The future of engineering in Africa will be defined by your ability to transform research and teaching into practical, impactful solutions. As we begin today's program, let us embrace a shared vision, which is to advance GFRP research, to strengthen academia industry collaboration, and to expand our impact beyond Ghana to the broader African region. On behalf of the Faculty of Engineering and the Civil Engineering Department, I once again welcome you all and wish you a highly productive and insightful forum. Thank you very much.
Thank you very much, HOD Engineer Dr. Produe. We are grateful to you. That's my boss. I'm in Civil Engineering Department, so my HOD. Let's give it to him, please. So I'll go straight forward to the introduction of dignitaries. So we have here of Gateka University, Engineer Dr. Tajani. He's a mechanical engineer as well. Then we have Engineer Festus Nayan, research scientist, Ghana Standards Authority. Then Mr. Emmanuel Otupa is also a research scientist, Ghana Standards Authority. And then I think we have an engineer here, the private man. Yeah, sir, you are welcome. It's you. Yeah, please. You are welcome. And then we have our noble presenters at the back, researchers, they are all at the back. Please, let's see your hands. Now, let me introduce Prof. Kankam. And everywhere that I have the opportunity to introduce him, I want to make it clear that Prof taught me. So those of us that I'm teaching here, I was mentored and taught by Prof Kankam. Prof is a renowned structural engineer, and he's been a professor, as some of us would say, full professor, for close to 30 years, if my memory serves me right. So it is not out of order. Hello, are you listening? It is not out of order to call him emeritus professor. You see him looking handsome. He's old. I won't mention his age. He's old. I'm nearing 50. And if he taught me some 20-something years as professor, you can imagine how the age he is here. And he's a very kind and nice man. If you have a good heart, you always look young as he is. And that's the kind of professor that I've known him for all these years. Some of the people that he's taught are also full professors that I know. So he can be deemed as an emeritus professor. So we have Professor C. Yeah. Prof, you are welcome. We are all grateful. HOD was taught by him. I was taught. A lot of people here, some in KUSC, all of us, the full professor, and then renowned structural engineers that you know, they were all taught by him. The polytechnic that we had, they drafted the syllabus. And so he's done so many. I don't want to talk too much, but I want you to know that we have a noble professor here. That's what I want you to do. So please, let's give it up for him. So I'll move on to the industry keynote presentations. Are we good to go? So, Dr. San, so I'll let Mr. Ivan start whilst we prepare the presentation. Muhammad Ashad. So, CEO for Viva Fiberglass, Mr. Ivan.
Thank you very much for this of this team and to have this chance to deliver some developments to the future of engineering of Ghana and Africa. Fortunately, fortunately for emerging material with academia, which is actually the advice of Ghana Institution of Engineering to us, which started in 2022. And now we are happy to declare around Africa that Ghana is the leading country. And yes, it's a really an achievement. But it didn't come easy. I want to stress to these young future engineers, don't wait for this easy whatever success that you expect to get at the graduation practitioners, and they are even using Viva Bar as a concrete reinforcement in their practical projects for more than 8 years. So now they are coming up after already using it on practice with some more scientific researches to show where else it can be used. So that's it. I don't want to talk more. I just want to encourage you to ask questions and be very critic, because structural engineering, civil engineering is all about not believing what you see, what you hear. It's all about finding out yourself. Thank you.
Thank you very much, Mr. Ivan. So just some few introduction before we start. Prof will come. Okay, so we have the HOD for Electrical Electronics Department, Engineer Dr. Bani. We have some faculty members here, Engineer Sasa, Civil Engineering Department. Engineer Bako is also the Civil Engineering Department. So I'll move on to Prof to give us a remark.
Right, thank you. And good morning, everybody. Okay, I'm also supposed to give a short keynote address, just as Dr. Ivan did. But I'll use the time just to point out a few things about glass fiber as an emerging reinforcing material, in place of steel or in conjunction with steel. You see, steel has been the conventional or traditional material for reinforcing concrete, right? It has some disadvantages and a lot of advantages. As an emerging material, glass fiber reinforced polymer also has several advantages. As a matter of fact, over steel, right? So, but as an emerging material, or as a material that has emerged, let me put it that way. The case is that the stresses in the glass fiber are low, and the fractions can be controlled. So the failure mode will be compression controlled failure mode, as the codes will describe. So when you have the compression failure mode, that one is more ductile, because the concrete is inelastic. Glass fiber is fully elastic. So if the concrete is going to fail, it is the concrete being inelastic. The failure mode will be gradual. And that is in structural engineering. That is what we want. We want the failure mode to be ductile, gradual, so that any occupants, be the structure can vacate the building, right? So we want that. So, but unfortunately, so I'm using the word unfortunately, the codes, especially the American code, ACR 440, allows, permits the use of both tension controlled failure mode as well as compression control failure mode. This is completely different from steel design. In steel design, the practice or the principle is always to allow the steel to yield. Steel should yield first, which is called the under reinforced design principle. The steel should yield first because the steel can yield. It takes time for it to completely fail, so the warning can be obtained. When is the steel? Because steel is ductile and its ductility is more than that of concrete, right? Unlike glass fiber. So there's implication, right? We have the desirable properties, but still, as engineers, when we are designing, we have to be conscious of the various properties. So it is very important to be aware of the properties of glass fiber very well. Now that we have the chance, as as Ghana, as Africa, and so on, we have to study it very well so that we can use it fully, use it fully in our um, construction. There are some areas, as I said, we should learn the properties very well. There are certain areas that need to be studied. Certain areas in glass fiber, I don't know whether we have it on the board, but one area, for example, is, for example, when we talk of compression of glass fiber, to study the compression strength of glass fiber, there's no standard method. So as students and so on come out as faculty members, let's find out how the standard that we can use. I'm saying there's no standard. So but people have done some studies where there's no accepted standard for testing the compression strength of glass fiber. So we need to look at that. The other areas are when you have some of the manufacturers are able to bend glass fiber into hooks and bends, so that we can have, we can improve upon the bond, right? Hooks and bends. The formula, American code, formula for determining the force in a bend is based on some empirical parameters that are not empirical. You have some parameters like the bend radius and the diameter of the bar, then the length of the bar, and so on and so forth. But studying the actual force in this is not known. So we need to find out. We need to study and come out with, if we have a bend of the hook, particularly at anchorages, we have to study, the forces in the bends. Then there is a problem of punching shear in flat slabs. These are also being proposed so some of these are being proposed by the course of practice, international course of practice, for more research into it. So even though in the developed countries, glass fiber has been used for maybe a few decades, they are still studying. There are certain areas that are not not known very well. So they are gray areas which have to be investigated. Right. So at KNUSC, we conducted a few, some research works, including the mechanical properties of glass fiber, and one of our presenters will come out with the findings that indicates, the strength, the strength being dependent on the bar size, which is not like steel. The strength is dependent on bar size. The modulus of elasticity is dependent on the bar size, and so on and so forth. Then the behavior of glass fiber in beams and slabs have also been studied. The bond of glass fiber, both anchorage and low carbon. Then punching shear in slabs. And then maybe finally, let me mention this. Okay, then behavior of glass fiber in compression in columns. Glass fiber in columns. And then maybe finally, reusing glass fiber. Glass fiber, maybe in a certain building, the building is, demolished, and you retrieve the glass fiber and reuse the glass fiber in a new construction. That has been studied at K University. And there are others. But some of them will be presented by the colleagues that we have, but some remember the team, we say team from K University. Some have graduated, others are continuing. So they are here to do the presentation. And we'll get to know more about the details and characteristics of glass fiber. So on this note, I'll end. And also, we also want to add that we are very grateful to ATU for hosting this forum for us. Thank you very much.
Thank you, Prof. We are also grateful for the insightful presentation. So we'll go straight to our next presenter, that is Dr. Salim Mohammed Ashad. Please, let's welcome him.
Good morning, everyone. So first of all, I would like to sincerely thank Accra Technical University for hosting this technical session, and also extend my appreciation to Professor Kankam, the university leadership, including the Dean, the Vice Chancellor, the Pro-Vice Chancellor, the HODs that are here, Mr. Ivan, the Director himself, practicing engineers, postgraduate researchers, and the students that are present. So as introduced, my name's Salim Muhammad Arshad. I'm a graduate civil engineer from Kenya, particularly the University of Nairobi. And today I will be presenting my research and evaluation work, focusing on mechanical properties, environmental durabilities, thermal behavior, and structural implications of the Viva bar that I have tested and conducted in Kenya. And it is truly an honor to present in a country where this technology is already well established and has been actively adopted over the past 8 years, because Ghana has played a very important role in the development and implementation of the Viva fiberglass bar within Africa. And much of the ongoing research and industry application has originated from here. Most of my sources, when I was doing my technical research, came from Professor Kankam and his researches. So thank you very much for that. So as engineers, we continuously design structures to resist multiple forms of loading and deterioration, like axial forces, bending moments. So in my presentation today and throughout this session, I will discuss the role of concrete cover, the fire and thermal behavior, the tensile performance under aggressive environments, the impact tests that I had performed back in the University of Nairobi, the beam flexural response, and and the engineering implications of the hybrid system that we currently have from Viva. So starting with this slide, which is the concrete cover, before discussing about the reinforcement itself, it is extremely important to understand the role of concrete cover, because concrete cover is the primary protection mechanism in reinforced concrete structures. It acts as the thermal barrier, the corrosion protection layer, and also a durability protection system, because in an instance of fire exposure, the external surface temperatures could go up to 800 or 1000 degrees Celsius. However, because concrete has relatively low thermal conductivity, the heat penetration towards the reinforcement usually occurs gradually as per how the code specifies. So for instance, steel and Eurocode specifies the standard protection according to the amount of time that is needed for evacuation upon occurrence of a fire, to prevent the collapse of the structure, which is sudden once the heat gets into the reinforcement. We can move on to the next slide. Okay. Okay, sure. Thank you. So this section basically emphasizes the previous slide, whereby you are able to see the calculations for concrete cover and how crucial it is and specific it is in the design, because this is what ensures the corrosion or the fire or the salt water does not get to the reinforcement. This is the protection of the reinforcement, of the fiberglass, of the steel reinforcement, of the other FRPs. So this is an emphasis of the concrete cover and design calculations. We can move on to the next slide. So moving on to my first test that I did at university level, which was the tensile strength testing under different environmental characteristics, trying to test the limits of the Viva bar. Because most of the research that I found from Ghana had already tested the basic tensile strength from Professor Kankam and the researchers. So I wanted to take it a step further and test it against high temperatures. And for high temperatures, I picked 240 degrees Celsius. And why 240 degrees Celsius, if you ask? Because this is the temperature at which the concrete cover is compromised and the cracking becomes visible. And at this stage, the fire is already reaching the reinforcement inside. Sorry. This is the stage where the fire is already reaching inside the reinforcement, which the reinforcement at this point would already be compromised. So I subjected the samples to high temperatures. Next was high acidic conditions, trying to test the corrosion of the material of the fiberglass rebar, because we all know steel reacts with the acidic conditions and it's eaten, it's chopped up when it comes to the acidic condition. I was able to concentrate a 0.1 molar sulfuric acid, achieving a pH of, I believe, 1.54. So very concentrated acid. Subjected the sample for 7 and 28 days to test for early stage corrosion and late stage corrosion. Then I moved on to high alkaline conditions, because we know the concrete is very highly alkaline. So I subjected it to concentrated calcium hydroxide, because the material properties could change once the fiberglass is submerged inside the concrete. So I did it as well for 7 and 28 days for the early stage curing and the late stage curing. And finally, I exposed it to salt water environment, because where I'm from a coastal island in Kenya, in Mombasa, whereby salt corrosion, the corrosion of the steel bars by the salt water is very high. You leave the reinforcement outside for 1, 2, 3 days and you start seeing rust on top, which in the long run affects the performance of the material. Upon all these subjection of the reinforcement to harsh environmental conditions, I can attest that there was barely the changes in in the tensile strength was basically between 3 to 5%, and all the samples achieved a minimum of 1,150 megapascals, with changes between 3 to 5%, which was not significant because the material is not corroded by the acidic condition, is not affected by the temperatures of 230 and 240 degrees, it's not affected by the high alkaline conditions, and also not affected by the saltwater environment like the steel reinforcement that we are using. Moving on to the next slide, which is the impact testing. And this section evaluates the toughness and sudden response, the sudden load application of the Viva bar using ISOD and CHAPI impact testing, because these tests are important because structures are not always subjected to gradual loading. In real engineering situations, structures may experience impact loading, vibration, accidental force application, debris loading, sudden stress. So these are things that should be catered for when you're looking at it at the material level before even putting it inside the concrete. Because the ISOD test, to be specific on the ISOD, it evaluates the impact resistance using a vertically fixed position, and for the CHAPI, it uses a horizontally supported specimen to evaluate the toughness through the impact energy absorption. And one important observation when I was doing this test is that the Viva bar did not fracture completely. It did not completely disintegrate, unlike the other specimens that are put in that machine. This behavior is important because it indicates the internal energy absorption. It also indicates the crack resistance and progressive failure characteristics. And for younger engineers here today and the students, one important concept to remember is strength alone does not signify structural performance. There's things like toughness, energy absorption, impact resistance, which are equally important because structures must survive unexpected loading conditions, seismic activities, wind loading, and other catastrophic failures that are unexpected. Moving on to the next slide, which took me a really great time. This was the beam loading test, beam flexion. So for this specifically, I casted 6 beams, whereby 2 of them were reinforced fully with steel. 2 other beams were reinforced with fiberglass, except for the links and U-shapes at the end. And the last 2 were reinforced with the hybrid approach that Viva is vouching for, the hybrid approach whereby in the lower members where there is high tensile strength, where there is high tensile requirement, I use the Viva bar, and then the top members whereby there's subjected to a bit of compression as well, I use the regular steel from the market. And as you can see, I left the beams to cure for 28 days before taking them out and putting them in the flexure machine. And the beam that achieved the highest strength when I took the sum was the hybrid beam, because this ensures that the materials complement each other, because steel contributes for the compression, the shear at the end, which fiberglass is not able to do as effectively. And on the other hand, the fiberglass does tensile strength better than steel and holds a much higher strength when it comes to tensile. So the hybrid systems, as I've said, benefits complementary material behavior, and it is a very important engineering aspect, because modern structural optimization does not necessarily involve replacing one material entirely. Instead, it involves combining materials intelligently so that each material contributes where it does best. And this is the fundamental philosophy behind the hybrid system. Moving on to the next slide. And this is a test that I've done, and I have an article on fire, comparing the fire exposure of steel reinforcement to the Viva bar reinforcement, of which, as you can see, the steel behaves predictably under elevated temperatures, which up to 200 degrees Celsius. And above the 200 degrees Celsius, when we get past the point where I mentioned earlier that this point where concrete starts to fail and crack, at this stage, the fire is exposed directly to the reinforcement. And this is where now steel's graph, according to the POH models and the Eurocode models, the yielding starts. And once the yielding starts and the temperatures continue to rise, steel's rate of yielding once exposed to fire is very high. So the failure is abrupt. The time for evacuation, which is 60 minutes, is usually for the concrete cover, that is for the design. But once the steel is exposed directly to the fire, steel no longer holds its ductility as much, because the graph of its loss of strength goes down drastically. As you can see, at temperatures at 200 degrees Celsius is when the yielding initiates and the stiffness begins reducing, and also deformation becomes more significant. And even taking the temperatures higher to 550 degrees Celsius, steel reduces its strength to about 60%. The deflection increases rapidly, and the creep becomes highly influential at this stage. By getting to the point of 700 to 1000 degrees Celsius, only a small portion of the original strength that cannot even is left. And this is where the building it's structurally unstable and it's collapsing at this point. And an important highlighted issue here
is the thermal conductivity of steel that I also wanted to mention. You'll see it on a further slide. Steel transfers heat very effectively. This means that fire exposure on one region can affect reinforcement temperatures across a large structural area. So even the unexposed regions may weaken due to heat conduction of the reinforcement network, and you'll be able to see it visually in the, I believe, the next two slides, and I'll be able to explain it better. Now, moving forward to the Viva fiberglass bar. So unlike steel, the fire behavior of the Viva bar is mainly governed by the resin matrix. This limits as you can see from the left side of it, whereby the low thermal conductivity as a property that I noticed when doing the article of fire resistance, the Viva bar is 100 times lower in thermal conductivity than steel. However, the Viva bar performance under fire depends heavily on two temperatures, which is the glass transition temperature and the decomposition temperature. Because at approximately 250 to 300, which is the same temperature where the concrete cover is compromised. That's why I keep on stressing on the importance of the placement, the spacing, the stools, and the concrete cover to protect the reinforcement from such catastrophic failures. But between 250 to 350 degrees Celsius, whereby the fiberglass bar has already been exposed to the fire. So at this stage, the resin matrix begins softening, and the stiffness of the material reduces, and also the bond efficiency starts to decrease. Raising the temperatures up to 400 degrees Celsius, the resin decomposition now becomes significant. The tensile performance starts to reduce rapidly because of the bond strength of the matrix. The fiberglass strands themselves, they are not affected by 400 degrees Celsius of temperature. They're very highly temperature resistant. And moving up above 650 degrees Celsius, the resin matrix now becomes fully disregarded. And one important engineering observation is that the concrete cover delays this disintegration process for the embedded bars, both for fiberglass and steel. And again, this reinforces the importance of concrete cover in the material. Now, on the next slide is what I was drawing from the fire analysis of steel and Viva bar that I have done, because this slide highlights one of the most important differences between steel and Viva bar on thermal conductivity, because steel is highly conductive, and once exposed to fire, the heat spreads rapidly throughout the reinforcement network, and it increases the system-wide thermal degradation because of the 100 times less conductivity according to the KMTC article. This heat remains more localized. For instance, one part of the slab is experiencing the fire exposure. There is no conduction that would lead to heat generation in a system-wide nature. And this does not entirely eliminate the degradation, but somehow changes and limits the heat effect onto one part of the slab, increasing the time for evacuation and increasing the time for people to be safe and secured inside a building that is experiencing fire. And from a structural engineering perspective, this becomes highly important when looking at localized fire mechanism and system level resilience. This is also the reason why hybrid reinforcement systems are becoming increasingly important in advanced infrastructure design. Moving on to the next slide, towards my now conclusion and recommendation. This research demonstrates that fiberglass reinforcement provides significant advantage in corrosion resistance, durability, sustainability, and reduced maintenance requirements. However, the most important conclusion is that no reinforcement is universally perfect, and good engineering design is not about replacing one material blindly with another, but it's about understanding behavior. It's about structural interaction. It's about environmental exposure. It's about long-term performance. And it is why us young engineers and researchers should take the opportunity to criticize the material, to look at what tests can I do? How can I improve on whatever I am working on? What technology is there that can be explored to increase the efficiency of our already built and placed structural designs? Because the hybrid philosophy, according to my conclusions, represents an optimized approach rather than a replacement strategy, because steel contributes in compression, shear, bending, redundancy, and also the established fire behavior that is already there. And the Viva bar, on the other hand, contributes in the corrosion resistance, the high tensile properties, higher than steel, the low thermal conductivity, and the improved durability performance. So these two materials, you have to see how they can both work hand in hand to achieve the best results. Together, they create a more balanced structural system. And this is where the future of advanced reinforced concrete design is moving. And leaving this alone, before I conclude, I would also like to say a few words to the upcoming engineers present here today, because engineering is a very wide field. And sometimes when I was a student and when I was a young researcher, I'm a young researcher as well, we think engineering is only about passing exams, attending lectures, and completing projects. But in reality, engineering has a much bigger scope than that, because it's about problem solving. Engineering is about innovation. Engineering is about curiosity. Engineering is about research. Engineering is about continuous self-development. And one thing I would strongly encourage myself and the audience that is present, and especially the students, is that you need to become more proactive very early. Do not wait until you start, do not wait until graduation or when you receive the paper to start building your engineering capability, because there are things that you can learn besides the curriculum. You can learn software design. You can learn the design analysis that is out there, the structural softwares that are used. You can visit sites. You can join research programs. You can ask questions. You can read research papers, like Professor Kankam has a lot of them, and he has a lot of research students. You can start from there. You can talk to practicing engineers. You can volunteer for projects. There's a lot that you can do to evolve you while you're still at university level. You can develop communication skills. You can, deliver technical reports, and you develop some sort of technical confidence that will increase your value besides the degree that you're getting, because the engineering industry in Africa rewards people who continuously improve themselves. And engineering as a whole has very many niches, because some engineers are excellent in structural analysis, some of them materials. It's a wide field. Transportation engineering, water engineering. So there's a lot that you can look into to develop yourself for further knowledge and further broadening of the mind, because there's no one who has studied everything and anything. There's always something you can add on. There's always some sort of value you can add on yourself. So these are the references that I have used. I decided to put them there so that if there's researchers who are willing to go through them or they need any further clarification, you can move on to the last slide as well. There'll be my details there. You can feel free to interact and ask questions. My contacts are there. My email is there. So, and again, to stress on the point home, research and innovation always begins with uncertainty. You're not always certain. When the Viva bar came to our university for the first time, it was a new material and it required a lot of research, a lot of demand. And I was the student who picked it up and decided to take this initiative to do extensive research on the material. So research, this is why research is very important, because it teaches us not to blindly accept ideas, but to scientifically evaluate them and understand their real behavior. And finally, I'll give you a takeaway home run. This is because for the students, your engineering degree gives you the foundation, but your growth as an engineer or a practitioner depends on your discipline, your initiative, your curiosity, and your willingness to keep learning beyond the lecture halls, beyond the classrooms, beyond the auditoriums. And the future of engineering in Africa will heavily depend on young engineers who are technically skilled, innovative, research oriented, and they are willing to push the industry forward. I had to make my presentation short. I have a research on fire article. I have an extensive research. I've just put it in a summary of around 10 slides, but it's a really thick book, and the engineers present or the students who are interested in the research, you can feel free to reach out, and I'll be able to help, guide, and share information together with the team, Mr. Ivan, Professor Kankam, and the other researchers that are here. We are willing to help and support. So thank you very much for your time and attention. Thank you very much. It's a pleasure to be here.
Thank you very much, Doc. So we'll take two quick questions from faculty members. So Engineer Dr. Bani.
Yeah, thank you very much. I was a bit curious about the Viva bar. You know, I'm an electrical engineer, and you know the ceiling fan, we use the steel. Can we use that one also for the hook, for the ceiling fan? Have you done any research on that?
For the hook, you use the regular steel that is there. Yeah, you can't use it for the ceiling fan because, yeah, you can't bend it. Yeah.
And we take the last one from Dr. Nyano.
Yeah, thank you for the presentation. So I think your last statement makes it a bit clear. This was a very compressed presentation because I was a bit worried that you never once mentioned the technical specifications of the samples you had used in your test, which makes it difficult to really understand the conclusions you are making. But the one I want you to really specify, did you measure the strength of the Viva bar at the TG temperatures between the 200 and 250?
For the temperature test, what I did is I had 3 samples of each, whereby one sample I tested it under the normal room temperature, and the next sample I tested it under the glass transition temperature, and the other sample I tested it under the other transition temperature as well. So I was able to come up with summation and of the total value divided by the original one to get the average model, which is why I was stating the inference is it was between 3 to 5% differences when it comes to the temperatures rising, because I left the samples to cool down and then put them in the tensile machine and then subjected them to the tensile strength test again.
Doc, are you okay? We have time for questions and answers.
Okay.
Yeah, thank you. So please, let's give it up for Dr. Ashad again. We have a special time for questions and answers, so we will do that. But now we'll take one presentation from George Otibuatin. Mr. George Otibuatin, the presentation is on mechanical properties of GFRP bars in tension. Thank you.
Okay. Good morning, fellow students. Good morning, Mr. Chair. Okay, my name is Charles Osaya Bebio, and I'm presenting on behalf of George Otibuatin, a researcher in KUST. Presentation, 5 minutes. Okay. Mechanical properties of the fiberglass reinforced polymer bar. Can you move on to the next slide? So the outline of the presentation would look at a background and then the preparation of our specimens, then the mechanical performance analysis, and laboratory results of the GFRP mechanical properties. Then we have in there the stress strain curves, and then the stress strain response of FRPs as compared to the steel, and then the proposed safety factor for GFRP and recommendation for design. Okay, so tensile strength is an important mechanical property of FRP bars, like already said, with high tensile strength. We will look at that, which allows them to effectively resist tensile forces in concrete structures. Okay, so the modulus of elasticity is another key characteristic of FRP bars. The modulus of elasticity of FRP bars is smaller than that of steel, which means that FRP bars are more flexible and have a lower stiffness compared to steel reinforcement. Can we move on to the next slide? Okay, so in preparing our specimen, or when the researcher was preparing the specimen, he had 18 total specimens of GFRP bars, and then what he did in the lab was that he cut 300 meters of the GFRP bar, and because the GFRP bar is said that the ends fracture when in compression, the researcher had to hook the ends with a 25 mm steel pipe, and then use epoxy glue to hold it so that we could do the tensile strength test. Okay, please, can you move on? So you have a picture, sorry, of the sample space. Please, back to the other slide. Go back to the slide. Okay, so you have a sample of the specimen with a grip on the right, top right, and then you have the universal tensile machine used to test the tensile strength. Okay, can you move on? Okay, so he tested 10 mm, 12 mm, and then 16 mm bar. And then what the researcher realized was that the strength of the GFRP bars decreased as the bar size increased. What it basically means is that if it's a 12 mm bar, the tensile strength of a 12 mm bar is higher than that of a 16 mm bar. And then we also see that the bars failing by rupture demonstrates significantly higher ultimate tensile strength than those that slip. So if you try to pull the GFRP, you realize that the strength is lower when you pull. Okay, please can we move on? Okay, this table also gives us the results of the GFRP mechanical properties. So for each diameter of bar, 10 mm, 12 mm, 16 mm, we have in Young's modulus of elasticity and then the tensile strength. So you realize that the 10 mm has a tensile strength. That's for modulus of elasticity. You have 1,193 newtons per millimeter squared, and then for 12 mm you have 1,030 newtons per millimeter squared, and that for 16 mm you have 866 newtons per millimeter squared, just to show that the smaller the diameter, the higher the tensile strength. Okay, the next slide, please. Okay, so this is a graph of the relationship between the bar diameter and then the strength. Can you move on to the next slide, please? Next one. Okay, here we have the stress strain curves of the GFRP bars. So the researcher realized, as earlier cited by Professor Kankam, that the GFRP bars are linearly elastic. So you have stress strain curve for the 10 mm when the GFRP ruptured, and then you have stress strain curve for the 10 mm bar when there was slippage failure. In both cases, you see that the GFRP bar is linearly elastic. Please, can you continue? Next slide, please. The same applies for the 12 and the 16. Can you move on, please? Okay. So tensile strength of different specimens of same size, as well as different test specimens from same bar, differs from each other, meaning that the GFRP is heterogeneous and anisotropic. Okay, so there's an equation for the rupture mode and the slippage failure mode. Please, can we move on? Can we move on? This graph gives us a comparison of the FRPs, a graph of the FRPs as compared to that of steel. Please, can you move on? Okay, so the researcher came up with a conclusion that the proposed partial factor of safety for GFRP based on literature that he reviewed, it's 1.52. We know that of concrete, which is 1.5, and that of steel, which is 1 or 1.1. But we are saying that GFRP, we are proposing 1.52. Can we move on, please? These are his recommendations for design. That in steel reinforced concrete members, design is conventionally based on steel yielding before concrete crushing, as earlier cited by Prof. Kankam. And then, but for GFRP reinforced concrete members, design for flexural capacity of a steel structural member, as recommended by the ACI code, is based on two principles or strength limit states, namely the tension control section. I think Prof. Kankam explained that. And then the compression control section. Then controlling limit state is determined by comparing GFRP reinforcement ratio with balanced reinforcement ratio, whereby both GFRP bars rupture simultaneously as concrete crashes in the flexural concrete member. So both design principles are accepted by the ACI code. Okay, thank you.
Thank you very much for presenting it on behalf of Mr. George Otibuati. Please, we'll take a break and then we'll continue with the presentation. So we take a break for 15 minutes. Please, students, hold on a bit. Our visitors will go first and then you come later. So please just be calm and be seated. Thank you.